surface charges. And the fields. Now, mathematical derivation is to understand how to calculate. That's all. I will always consider standard surfaces in the coordinate systems. Suppose I will take two things simultaneously. I have a rectangular surface. Extending an x-axis from minus a to plus a. Extending an y-axis from minus b to plus b. Concentrate. This is the center. Above this particular census axis of this surface. At a height h on z-axis, on the axis is z-axis here. Later on, only these calculations are there. Of the axis points, we don't calculate because they don't come into standard procedures. We can do. We know that, right? But we'll consider now the axis, some point on the axis. How to calculate? Here, the surface charge density rho s is given. The surface is the surface on xy plane, extending along x from minus a to plus a, along y from minus b to plus b. Now what is that I have to do? I have to divide this surface into infinitely many infinitesimally small differential surface elements in this particular plane. And that differential surface element is at any x, y, 0 dx dy. At any x, y, 0 dx dy. Please note this. The charge on that differential surface element is rho s dx dy. I want to calculate the electric field intensity at this particular point, which is at a distance h from the center of it along z axis with coordinates 0, 0, z. The radius vector from a general point on the surface to the point of interest is minus x ax, because the coordinates are 0, 0, h. Final coordinate 0 minus initial coordinate x minus x ax minus y ay plus h az. Because of which the electric field intensity dE bar at that point, because of this general element, is what? Rho s dx dy. Of course, by 4 pi epsilon. R bar is minus x ax minus y ay plus h az by x square plus y square plus h square whole power 3 by 2. Check it once. I told you that this is the engineer's job. Consider the appropriate general element on the surface. Get the charge on that differential element. Get the vector from the general element to the point of interest, point of observation. use that along with the medium constant epsilon to first write the differential electric field intensity. Then check it once. E bar is equal to integral minus b to plus b, integral minus a to plus a. I have to consider such elements everywhere in x from minus a to plus a, in y from minus b to plus b. dE bar, which is having dx dy. Since, check it, in the case where you have a perpendicular bisector of the line joining two equal charges q and q at this particular point, the forces are of equal magnitude because it is a perpendicular bisector. This theta is same as this theta, because of which there will be only non-zero field component along the perpendicular bisector. Along the line, net field is 0 because there are two equal and opposite components. For every differential element that we consider in the course of integration, I would have considered a symmetrical element passing through the foot of the perpendicular, leading to this case where its horizontal components are what? X and Y components get cancelled out. Any X and Y components because of this element get cancelled out by the X and Y components of the symmetrically situated element. Anyway, in this, X component integral is X by root of X square plus Y square plus H square whole cubed. Odd function in X. In symmetrical limits, it is 0. Y component, Y by something, odd function in Y, integral in the symmetrical limits is equal to 0. Because of which only Z component is to be integrated. And that Z component, when I write, is of the form what? Rho S H by 4 pi epsilon. Rho S H by 4 pi epsilon. 1 by x square plus y square plus h square whole power 3 by 2 dx first, dy then. Look at the integral Az only. If I were to consider the plane on xy plane, let us say this is xy plane for me, in which y goes from minus a to plus a, z goes from minus b to plus b, and my point is on x-axis at a distance h. I would have considered the element on xyz plane dy dz. Correct? Y going from minus a to plus a plus z going from minus b to plus b. On this, the coordinates are 0, y, z. This point is h, 0, 0, because of which it will be hax minus y ay minus z az. Here, which component will be there? Only x component will be there. Components parallel to the surface will not be there because For every element, there is a symmetrically situated element that cancels out the y and z components of the field created by the earlier element. Check it once. When I want to integrate it with respect to x, y square plus x squared are constants. Substitution is x is equal to root of y square plus x squared tan theta. Then it will become integral minus b to plus b. Rho s h by 4 pi epsilon. What will happen to this integral? Can you tell me? Dx is equal to root y square plus h squared secant square theta. In the denominator, it is y square plus h squared into 1 plus tan square theta is secant cube theta. What will remain? Dx is root y square plus h squared secant square theta d theta by y square plus h squared into 1 plus tan square theta whole power 3 by 2, because of which it is rho s h by 4 pi epsilon integral minus b to plus b 1 by y square plus h squared integral cos theta d theta secant square theta by secant cube theta, which is sin theta. What is that sin theta? Sin theta is, because my substitution is tan theta is equal to x by root of y square plus h squared. This is theta. Sin theta is x by root of x square plus y square plus h squared from minus a to plus a. It is 2a by a square plus y square plus h squared, right? This is 2a by root of a square plus y square plus h square dy. This is for sin theta integral. Now the way in which you have to integrate is definitely is what? Y square plus h squared is equal to a square tan square theta. And then you have to substitute for everything and evaluate it. Here, what is important for this is the integral formed. If it is infinite surface charge, what will happen? If it is infinite surface charge, the integral will become rho s h by 4 pi epsilon. Please concentrate now. Integral minus infinity to plus infinity. I'm looking at this integral only. 1 by y square plus h squared in the limit theta, it would have been minus pi by 2 to plus pi by 2, correct? Sorry, not there here. Integral minus pi by 2 to plus pi by 2 cos theta d theta. Which is equal to 2. Correct? This is dy. This is equal to 2, because of which it is again Az. Rho s h by 2 pi epsilon integral minus infinity to plus infinity 1 by y square plus h squared ay dy Az. The integral of 1 by y square plus h squared dy is what? 1 by h tan inverse of y by h from minus infinity to plus infinity, which is 1 by h into tan inverse of infinity is pi by 2 minus of minus tan inverse of infinity is pi by 2 plus, which is pi by h. Because of which the total field quantity is rho s h by 2 pi epsilon into by h Az, which is rho s by 2 epsilon into Az. If it is infinite surface charge, extremely important point. If it is infinite surface charge, the field at any point above or below becomes independent of h. Distance will go. If it is finite, distance will be there ultimately in the final expression also. For me, infinite line charge, rho l by 2 pi epsilon rho, a rho. And rho s by 2 epsilon a n, normal component to the surface. Az is now a n, are extremely important things for us. Rho s by 2 epsilon. I'll come to the same point through this. Check it. No, definitely we'll be ready. I will be ready to extend the discussion and then repeat it also if it is required, because these are the very, very important procedures that we should be masters of. Suppose I have a circular disc of radius a. Circular disc of radius a with rho s as the charge density. I want to determine the field at any point on its axis at a distance h. I will consider this circular disc charge, surface it is, on z is equal to 0 plane. And axis as the z axis, naturally. Then, at any rho comma phi, I need to consider ds, that is rho d rho d phi is what is a rho d phi. If you vary rho by d rho, one side is produced without changing phi on the circle of radius. We will on the same line d rho. Keeping rho constant, if you change phi by d phi, it produces rho d phi as the side length. Rho s is surface charge density. At any rho comma phi, z is equal to 0. Whenever I want to determine the electric field intensity because of this disk there. I need to consider the electric field intensity because of this element. For that, I need to define the vector from the element to the point of interest. Because it is at rho, this is minus rho aero plus h az. Correct? Minus rho aero, go back to origin, then go up plus h az. Because of which the electric field intensity again in this direction along the radius vector is what? Rho s rho d rho d phi divided by 4 pi epsilon vector minus rho aero plus h az by rho square plus h square whole power 3 r bar divided by mod r bar whole cubed. In this also, because for every element that I consider there is a diametrically opposite element, there will be no radial component for a circular plane. And the total electric field intensity, the E bar is this. E bar equal to what? Rho s by 4 pi epsilon. H also is there. Integral rho d rho d phi divided by rho square plus h square whole power 3 by 2. Rho from 0 to a, phi from 0 to 2 pi az. Integral d phi is 2 pi, which is equal to, the order doesn't matter, rho s h by 2 epsilon integral 0 to a rho d rho by rho square plus h square whole power 3 by 2 az. Integral d phi, only term, integral 0 to 2 pi is 2 pi. That went off. How to integrate this?
Substitute rho square plus h square equal to p.
Rho square plus h square is equal to t. Substituting rho square plus h squared is equal to t. 2 rho d rho is equal to dt. So rho d rho is equal to dt by 2, which is rho s h by 4 epsilon. Integral t is equal to h squared to a square plus h squared dt by t power 3 by 2. Correct?
Yes, sir.
T power minus 3 by 2 plus 1 by what is the value? Rho s h by 4 epsilon 1 by root t. Correct? T power minus 3 by 2 is to be integrated, plus 1 is t power minus half by minus half, which is minus 2. Correct? From h squared to a square plus h squared, which is equal to what? Rho s h by 2 epsilon into first lower limit 1 by h squared, correct only, minus because it is minus sign.
Sir, 1 by H.
1 by H minus 1 by root of A square plus H squared AZ. This is the field intensity at any point on the axis of a circular disk of radius A having the charge density of rho s. What is the field intensity if radius A tends to infinity? If it is infinite surface charge, then 1 by root of A square plus H squared become equal to 0. And we'll give what? Rho s by 2 epsilon AZ is E bar. The limiting case. When I talk about infinite surface charge, it can be rectangular with dimensions tending to infinity or circle with radius tending to infinity. In both cases, we got this E bar is equal to rho s by 2 epsilon. Very, very important for us to get into boundary conditions, because of which I'm talking about it. It was same whether I basically determine the field because of infinite surface charges, the rectangle with infinite dimensions, or circular disk with infinite radius. The electric field intensity comes out to be rho s by 2 epsilon only.